Welcome back to Applied Materials and Corrosion. Today we're going to look at the oxide layers or the corrosion layers on metals. So first of all we're going to do a bit of demonstration or see whether that works. So what I'm going to do is I'm going to take this blade, which is a steel blade, one assumes, and see that it's generally shiny. It looks shinier to me than it does to you. Let me take the shinier side. They're both the same. Yeah, that looks quite shiny to you. So then I'm going to heat it up and we will see what happens. So let's get it close enough to you. So what you can see is what appears to be a blue colour on the end of the blade and a line of rainbow-like colours, but it's not quite a rainbow. Yeah, it's a bit close to be a rainbow. And it looks like there's some kind of transition. Let's try that with another one, which I've put down somewhere. Here, we'll try it with this, which is a piece of scrap that I found lying around. So the same, let's do that side. Is this going to work? It's difficult to get this one as hot because it's thicker. It's now glowing orange to me. Might be to you. We're going to let it cool down so that I don't burn myself. And move it up close to you. We're going to have to do something with the lighting. It's a bit difficult to get this to work. That's the best. So what you can see is what appears to be a lighter colour at the end, and then it goes blue, and then it's orange, and in between orangey, straw coloured, I think they call it. So what can we imagine or deduce from that? We've got a metal, let's call it iron, because it's mostly iron, it's steel, and we've heated it up to a very high temperature. So it's hot at this end, and it's cooler at this end where we're holding it. And then it generates a set of colours. What we know about iron is that it reflects light. So that will be our light, and we're looking at that light reflecting back. And we know that it forms an oxide layer that is somewhat complicated. Let's imagine it initially as a simple oxide layer. So we can imagine some kind of oxide on the surface, and then we will end up with a normal, relatively understandable physics phenomenon that the beam that reflects off the top of the oxide layer and the beam that reflects off the bottom of the oxide layer, and also the beam that reflects doubly, but that one's very weak, will all come out parallel to each other if the top and the bottom of the oxide layer are parallel, which means that the thickness is constant. If they do that, then some colours, depending on the angle and the thickness, some colours will interfere with each other, and some colours will constructively interfere with each other. So some of colours will be destructively interfering and other colours will be constructively interfering, and so we will observe a colour. We would observe an apparent colour depending on the angle and the thickness. What we've observed here is if we heat up this end, we get one color here, and then we get some kind of transition to normal, which we can imagine is very much like there being a thickness that depends on the temperature that our metal got to, because it was hot at the end, and obviously I was holding it somewhere else, so that wasn't so hot there. Also, the flame isn't that big, so it's incapable of heating it up all to the same temperature. So that gives us a piece of background information that we now would like to analyze and try to work out whether it makes sense, and maybe come up with some theories about it. Okay, so let's have a look at this. We've got our iron with these red atoms, and we've got our iron oxide, which is a mixture of iron and oxygen, and we've got oxygen on the outside, and we've got it at some temperature. What we have presumed is that if we heat it up, it will grow a thicker oxide layer, and that will be determined by the temperature that we get to. And we imagine that it will get thicker if it's hotter, because that makes more sense. So how can that be the case? Well, what forces do we have here? We've got oxygen coming along, and the oxygen is trying to oxidize the surface. So if we put an oxygen right on the surface here, so we've got an O2 here, then we're trying to give electrons to it, like that. We're trying to give electrons to it from the surface. And the iron 0 is also, obviously, it could donate electrons into there to become iron plus. So that is the direction of the electron flow in this direction. This is E minus is going in this direction. It will be making our layer thicker, and then we end up with a problem. And the problem is that the oxygen 2 minus that we've made on the surface, so let's make that into an O2 minus, is stuck out here, and the iron 2 plus or 3 plus, depending on which it is, whoops, I've drawn that in blue, is stuck in here. So we've got this one, and we've got this one, and they really should be coming towards each other, otherwise we haven't got iron oxide. So until that they can combine with each other, we have generated a negative charge on the outside and a positive charge on the inside. This should be familiar with the electrochemistry that we have. So in our electrochemistry, we had a simple case, we had copper, because the advantage of copper is it doesn't have any, whoops, that's a bit ugly. So the advantage of copper is it doesn't have any oxide on the surface if we have the correct conditions, and it's relatively stable and we don't have to worry about it too much. So we've got copper, we've got a solution out here, and the copper is turning into copper 2 plus and going into solution. And as it does that, this electrode becomes more and more negative. And so if we put our copper electrode into solution, we end up with a voltage on our electrode, a negative voltage on our electrode, and then no current flows. So we can detect that. That was what we were doing last time. That's what we will do. We'll do it with, we might do it with copper, we might do it with iron. So we put a metal into solution, ions dissolve into solution, and it equilibrates. So at some point, we've got the copper depositing at the same rate as the copper is coming off, because the copper electrode has become negative compared to the solution. This is the same as is happening here, except that we've got a vacuum out here, or air. We've got air out here, and we've got metal in here, so we can't easily get rid of this charge, but it's stuck at the surface. Our oxygen has a local charge of 2 minus, so we've charged up this surface compared to the inside surface. So if we now simplify the diagram to a block so that we don't have to worry about all these atoms, it becomes a little bit easier. But while we've got this, we've got to think about the atoms hopping through, which you're sort of familiar with from metallic materials. This model is a little bit confusing because we would have a negative charge out here, which is not very likely to happen because this is more reducing. And we've got a positive charge here, which is more oxidizing, and obviously that is the wrong way round. So something is not quite working. Let us think of it in a bulk way, because I've drawn a bulk now. If we've got a bulk condition, we've got iron in here, iron 0 here, and we've got oxygen on the outside. And so we could draw a graph of the oxidation potential across our sample. Let me rub out some of the inside of the sample so that it's not in the way. Let's rub out this. So if we imagine the most oxidizing to be out here, that would be the oxygen, and that's constant obviously. We imagine the iron to be the most reducing, that's in here, and we would expect some kind of transition between the two inside the oxide layer, because the oxide layer is the only thing that is resistive. It's resistive in terms of electricity resistive. Electrons can't get through it very easily because it's not a conductor. Inside the iron, obviously we can't have a difference in electrochemical potential because we've got only iron and it's all conductive. And outside is a gas, and so everything's moving around, so it's the same as a liquid in that there shouldn't be a distribution very much. There might be close to the surface where things are being lost, but there shouldn't be much of a distribution of oxidation potential there. So that makes sense. We will get onto the different types of oxides in a bit, so we will think of it first of all as a single oxide, just one particular type. The problem with iron is it has several oxides, so they don't behave quite the same. But let's first of all imagine that it's got one on. So something like aluminium has a single oxide layer that is just got one chemical formula, and it's very resistive. So then we would expect a single resistivity, and the resistivity is not just to electrons, it's also to ions. And so those ions that were on the surface and on the inside can't get through very easily, and so we would expect there to be some kind of change. If we heat up our non-conductor, then we would expect it to behave like a normal non-conductor. So if we've got a conductor and we heat it up, it gets more resistive because electrons can't move so easily. They're kind of being hit into atoms and they're not going in the right way. But if we're in a non-conductor, then we increase the conductivity, or we reduce the resistivity if we heat it up. The practical part of this would be the ionic resistivity. So if we heat it up, the ions have more energy and the lattice has more energy. And as you'll know from either metallic materials or non-metallic materials, they're moving around inside their positions in the matrix, and they can squeeze through. Interstitials can pop through more easily at higher temperatures, which would mean that we would expect a lower angle because the resistivity determines this angle. The more resistive it is, the higher volts per meter it can support, and so we would expect a higher angle. And the less resistive, the hotter, the lower the angle, and we would expect it to be going to the same place, so we would imagine that our oxide layer would get thicker. So we can model our oxide layer like that, and that is fine, it works perfectly well. It does generate an interesting question, which is, do the ions move in or do they move out? If they move in, then our metal ions on the outside, metal ions on the inside, the oxygen ions on the outside are going to move all the way in and react with the ion at the interface. That is entirely possible. And the other possibility is that the metal ions go all the way through and react with the oxygen on the outside. Obviously, both could happen, but it could be dominated by one of the two species. That's most likely to happen if one of them is way bigger than the other one. The metal ion is often the smaller of the two, but it isn't always. Depending on what we have on the outside, it might not be oxygen. But what species are going to move inside this? We can imagine there's a possibility that molecular oxygen could make it through. It's relatively big, so it's comparatively unlikely, but if it was a small atom, it might be able to get through. We can imagine that iron 0 could make its way through. we can imagine that iron 2 plus or iron 3 plus could be trying to move through, because they vary in size and they vary in oxidation potential. So maybe we should think about what the oxidation potential is going to be, and if we look at this, we can see we've got a difference in concentration, a difference in voltage because we had a resistance, and so we can imagine that there's going to be a difference in oxidation potential. The oxidation potential of our iron 0 is obviously on our pour-by diagram at the bottom, and the oxidation potential of gaseous oxygen that's hot is at the top of our pour-by diagram, and there's some transition in between, so we would imagine that there would be different oxidation potentials in between. This line would also represent the redox potential of the position inside our oxide layer, which means that we can get to the next part, that if we're looking at an iron oxide layer, the iron oxide on the surface is going to be mostly iron 3, and the iron oxide at the bottom is going to be mostly iron 2. And so we will end up with a layered structure of oxides between the iron 0, the iron 2, and the iron 3, with the iron 2, iron 3 in between. So in a massively simplified way, we could draw lines on here and say at the bottom we've got iron 2 oxide, FeO. In the middle we've got magnetite, Fe3O4, which is iron 2, iron 3 oxide. And on the surface we've got Fe2O3, which is iron 3 oxide. In reality, there isn't a strong border between these because there are other states. But depending on what the element is, what the metal is, we could end up with borders in between where we would see a phased boundary, because the crystal structure of these are different. So some of these do have borders, some of them don't. In iron, there are a lot of oxides, and so some of the interfaces are smooth. There's a wide transition, and some of the others are not. But we then see a complex oxide structure, and the iron oxide here, for example, is held at this state, in this iron 2 state, because of the oxidation potential at this position, because the iron is reducing it and the oxygen is oxidizing it, and so it happens to be balanced for that. So thermodynamically, it's kind of temporarily stabilized. Locally, it's thermodynamically stable, but it's only thermodynamically stable because the iron is drawing it down and the oxygen is pulling it up, so the whole system is not stable. It will eventually oxidize. It just takes a very long time because the resistivity of this oxide layer is such that everything is locally happy, so very little happens. It's very slow. So what happens if we go into contact with the solution? Taking it very simply to start with, we've got something like this. We've got zinc oxide, and we've got some water, and now we're going to play with the external potential. We can apply a voltage to the zinc in some way. Sorry, my N is wonky. We can apply a potential to the zinc, and that will motivate the zinc to move or motivate the oxygen to move. And we've got some zinc oxide. It's probably got some hydroxide on the surface, but we won't worry about that too much right now. So our zinc is going to try to reduce the zinc oxide, because it's not its job, but it's trying to donate electrons to it. That would be electrons going in there that would make zinc plus, but it's also going to form interstitial zinc atoms, which are going to be stuck inside our zinc oxide. So that is an error. It's a point defect inside our zinc oxide. On the outside, zinc oxide has a tendency to form oxygen over extra positions effectively. So it tends to over-oxidize. So we've got, let's make them a different color. We've got oxygen positions on the outside, which are also point defects. So we can have in our zinc oxide both possibilities. The oxygen positions are comparatively rare. There are not very many of those, depending on how we've made it. In water, there usually isn't any. But we're just including them for completeness. If we take our zinc oxide and we apply so we want to make it corrode, we apply a positive potential to it to make it corrode, then we are going to be trying to pull electrons in this direction. We're trying to pull electrons to our positive electrode, allowing the zinc to disappear off into our solution. Then we can pull the electrons off the zinc as they come away, so we're going to make that easier for us ourselves. But the problem with the zinc is it's not going to be motivated because it's not charged, so we're not going to motivate it to move faster with our positive charge because it's not charged. We're going to be trying to make these move. What we should know is that we take our zinc or our metal, we put it into water, because this was water, so electrolyte. It has to be called an electrolyte because it has to conduct. If we apply a field to it, if we change the potential on here, we're effectively modifying that with a non-conductor, with an insulating layer. So the voltage, the potential, the redox potential that the electrolyte sees is not the voltage that we put on our electrode. There's effectively an electrode, a resistor in series. Let's put it in there. So we've got our metal, we've got a resistor, and now we've got the surface. It behaves pretty much like a perfect resistor. So we've got a fairly simple system. If we imagine our electrolyte to be doing nothing, if we try to do stuff, if we try to draw current, then our electrolyte will start to behave as a component in our electrical system as well. But if we do nothing, if we just observe the voltages, we can see there is a voltage, well, there's a voltage drop across our oxide layer. Obviously, for the same reason, because it's a resistor, because it behaves as a static resistor, then it can only generate a voltage drop, a difference in voltage, if we're trying to draw current. But unfortunately, in reality, we can only measure voltage while we're drawing a little bit of current, so we will always get a little bit of change. So yeah, it's going to be complicated. It depends on the relative conductivity of the electrolyte and the relative and that of the oxide layer. So on a stainless steel surface, for example, where the oxide layer is very thin and reasonably conductive, we don't see very much effect. And on an aluminium surface, the aluminium oxide layer is reasonably thick, although it's not that thick, but it's quite resistive. Then we see a big difference between the electrical potential of the metal and that of the electrolyte. Remembering our pour-by diagram, the zinc typically is reducing compared to the electrolyte. It's actually below the potential where we would reduce water and make hydrogen. So if we put zinc into water, we should make hydrogen, but we will generate a zinc oxide layer, which is resistive, and the resistivity will make the corrosion, the oxidation of zinc to form zinc oxide, and the reduction of water to form hydrogen. It will block that reaction, or at least it'll slow it down, because the faster we try to drive it, the more current we try to drive across our resistor, the steeper this angle, and so the thicker, the thinner the zinc oxide has to be to block the reaction, because as long as we push the voltage here to a suitable position, our reaction will stop. But obviously we can't stop it completely. We can slow it down to a position where this resistor is providing enough voltage drop. Okay, it's upwards in this case, but it's providing enough voltage difference so that our electrolyte is not doing very much. If we consider that in terms of corrosion, we can measure the amount of corrosion of a zinc surface in millimeters per year, micrometers per year, sorry. It's not very fast. In some electrolytes, it's faster, but in normal conditions in the air, it's very slow. What this means is that our zinc oxide is reasonably good at resisting positive oxidation, and zinc oxide is pretty good in water. We can molest it, we can allow it to become a little bit positive, and it resists fairly well. Nothing happens. But what happens if we make it negative? If we make it negative, we've got a problem, because our negative electrons, effectively, are going to try to reduce. They're trying to reduce some of this zinc oxide. They're trying to jump onto some of the zinc and make it into zinc 0, and that will make more of these zinc 0 positions. What do we know about, oops, sorry, I've drawn it in blue now. Let me draw a black one. What do we know about zinc 0 positions inside a zinc oxide crystal? Well, a zinc 0 position has 2 extra electrons compared to the normal zinc that's in our zinc oxide, and so it behaves as a normal dopant. It behaves as a negative dopant, and so this zinc can donate electrons, and they can move. They can hop onto this zinc, and they can hop out. It behaves as a semiconductor, which means that the conductivity of our zinc oxide is going up if we force zinc into it. So the more zinc that we push into our zinc oxide, the more it's going to be conductive, the more positions we happen to reduce inside our zinc oxide, the more the zinc oxide is going to conduct, and that is not going to make the zinc corrode anymore, because we're actually reducing it. So we're actually protecting it from corrosion. So it won't make it corrode faster, but it does mean that our zinc oxide is not doing the job of protecting it. It's becoming more conductive. We will see why that's a problem when we see a state where metal oxides are forced into reverse, effectively. They're doing the wrong thing. They're not oxidizing, and then zinc oxide does not protect. It's not the only oxide that doesn't, but it's a good example. So what happens in a more dynamic situation where we take a metal and we put it into an electrolyte and try to see what happens? Well, if we take our metal, first of all, there's always going to be something on there. Unless it's a noble metal, there's going to be something on the surface, so we have to do something about that or just live with it. Our starting condition is not going to be 0. Then we will start to corrode our metal. We'll start to form a metal oxide, probably, or hydroxide by reaction with our electrolyte. So we will build a layer, and the rate of that layer growth is going to be fairly quick to start with, but now we're going to be making it slower and slower as it gets thicker. So we're going to be effectively lowering the voltage at the interface, and then we're going to drive a reaction between our electrolyte and the oxidation potential of our metal. So the difference between those is going to drive our reaction, which allows it to go. And the steepness of this depends on the resistivity and the thickness and the current. So then we can effectively build up an oxide layer, but it will slow down as it gets thicker and thicker, because the driving force is the difference in energy and difference in electrical potential between these two. So it's going to go slower and slower, or in the terms of moving through the ions moving through the oxide layer, the potential is also getting lower and lower, so they can't move as fast. If we make our system a little bit more complicated, we can imagine that the metal oxide is dissolving into the electrolyte. So if we have something like iron or even aluminium in slightly salty water, the zinc in somewhat salty water, we will be able to dissolve it eventually So we will have loss of thickness. So now we've got a process which it becomes a dynamic equilibrium. So I'm hoping you know what a dynamic equilibrium is. This oxide layer is growing thicker because the oxide is reacting effectively. The metal is reacting with the electrolyte. It's growing a thicker oxide layer, but it's also shrinking because the oxide layer is becoming ions and dissolving into the electrolyte. So we've got two opposing processes forming an equilibrium, but it's not a proper equilibrium. It's a dynamic equilibrium. It's also not even a proper dynamic equilibrium because the metal is continually ending up in the electrolyte, but the thickness of the oxide layer appears to be constant because the thickness is coming from the back effectively and the dissolution is going out to the front. In this case, we can still see a stable state, a steady state, but it's not a permanent steady state, and this is what we typically aim for on our pour-by diagram, which brings us back in a circle to the diagram that we had before. So here is the pour-by diagram of iron. It's another way of looking at it, and this is what I want to see at this point. We can see if we were at a pH of 7, which is where my weird magnifying glass is. I should really change that, but I'm not entirely sure how to. If we look at this at pH 7 and we go up to here, we can see that if we have a low enough voltage, we can reduce iron to iron 0 and it was thermodynamically stable. If we sit at here at about minus 0.4 volts, we can see that we're going to lose our iron as iron 2+ ions directly into solution. That means that our iron will be corroding directly into solution and it will be very rapid because there is a clean metal surface with nothing in the way and the iron is dissolving completely off at that potential. As we go up in potential, we see something weird happens. Suddenly we go back into a region where we make an oxide, because we can now make an oxide faster than we're making this iron 2+, so we jump into this region and cover the surface of our iron with iron oxide, Fe2O3, that's iron 3 oxide. So we've gone from the iron 2 region to the iron 3 region. In the iron 3 region, the oxide is much more stable. Just at this pH, iron 2 oxide is soluble, completely soluble. Iron 3 oxide forms a solid. So we end up stuck here. And then we will build up an iron oxide layer and suddenly the reaction will stop. So if we do that experiment, which we will do, take some iron and we increase the potential, what we would expect to see is no current flows until we get up to here. Then we can make iron dissolve, and it will dissolve fairly quickly because there's nothing stopping it. Then it'll suddenly drop down. Then our current will go low as we increase the voltage until we get here, and then we'll suddenly generate current again. As I said before, this iron oxide will be dissolving on the outside and forming on the bottom, so we'll get some current probably, but it will be limited by the dissolution process, and it will be dissolving either down here as iron 2+ or up here as this iron 3+ oxide anion. If we get past here, we will end up dissolving it faster again. So we can end up with an interesting shape of our voltage curve because we have a passive region where our iron, in this case, is covered with an oxide layer. The interesting thing about iron is if we go up in pH, it becomes more stable. At high pH, iron doesn't really have a window. There's a little tiny iron here, but most of the time it's stable up to here. Then it becomes soluble as this other iron, anion. If we make it really acidic, so if we're right down at really low pH, then we have no chance of stabilizing our metal at all. It isn't stable at all. So we don't want to go in that region, or at least iron is never stable down there. Remembering that this pour-by diagram is a thermodynamics diagram, so it will tell us what would happen after infinity time, and we're misusing it to tell us about what will happen over shorter periods, because we've got, oops, I've done it again, we've got a dynamic equilibrium, we've got it's actually the wrong word again, we've got an equilibrium that is not constant, it's not a thermodynamic equilibrium, we've got a kinetic process going on where the oxide is being fed from the bottom with iron, and it's losing iron into the solution, either as FeO4 2- or as Fe2+, or if we get over close to this line, it's getting lost as iron 3+ into solution. So we're losing our oxide, but if we are in this region, our loss of iron will be slower than if we are in this region here, where it can go straight from the metal into the solution. Some of these oxides will be better than others at protecting the surface, and so we would be interested in whether some of these are going to will protect our metal better. What you can see here, reminding us of the situation we had before of different oxides on the surface. So if we look at this cut, let's call it 10, pH 10, we can see we've got iron 0, then we've got iron OH2, which would be stable if it can get onto the surface, but it's unlikely to be there. Then we would, so if we waited forever, that would be what we would get. That would be an iron 2 salt, but obviously we're going to form iron 2 oxide really close to our interface. If we go further out, we would see this magnetite, Fe3O4, and then we would see iron 2 oxide. So we would see exactly the same case going through as electrode potential through our surface to our iron. This is iron hydroxides, which are also stable, but we have to keep them inside a relatively narrow range of potentials to keep them stable. If we're too oxidizing, they will oxidize up, and if we're too reducing, then we'll lose them to iron. And this is what it looks like as a current to voltage curve. So I'm just going to draw I on there badly. I've got the current on the vertical axis and the voltage on the x-axis. So as we increase the voltage, the current doesn't change until we pass that iron to iron 2+ transition where the pen is now. Then we get current that increases as we increase the voltage to a very high value. Typically these are done on or drawn on a logarithmic scale, so this would be a huge current compared to the rest of the current. It goes up very quickly. And then when we reach that point where we start to make oxides, the current comes right down. It doesn't go to 0 because there is then a passivation current where we're making the oxide at the speed that it redissolves. So we can keep that constant for a relatively long time. We can keep it constant for a relatively large range of voltage in this case. But eventually we cross back over into the other range when we are making the anions directly from the surface, and so our current increases again. We start to cause damage to our oxide layer effectively. So that is a little bit of an introduction to passivation on metals. We will try to do that as an experiment next time. I'll try to get some measurements of it as soon as I can.